Welcome to Artificial Intelligence and Foundation Application class. Today we'll be looking into constraint satisfaction problem, particularly how to solve constraint satisfaction problem. In earlier lectures we have seen, given a problem, how we can model the problem using constraint satisfaction problem strategy. Today we will elaborate on how to solve the problem. So in order to solve a problem, we have to follow a set of steps. The overall strategy to find out a solution is as follows. So what we need to do, we need to create a constant satisfaction graph, what we call CSP graph, and then what we do, we go for constraint propagation, and we also then search for a solution. So these three are the broad steps that we need to follow. So now we'll look into what is there in each of those steps quickly. So for CSP graph creation, what we do, we create a node for every variable. So when we try to model a problem in CSP, we know we have to define a set of variables. So we have a set of variables P. For every variables we have domain D, and we have a set of constraints that that the variables needs to satisfy, and there can be some optimization function. So this four component that we have seen in our earlier lecture. So now what we will do, for every variable we define a node, and all possible domain values are initially assigned to each of those variables. So if I have a variables x1, x2, x3 and so on, and for every variables we assign all the domain values, values for each of those variables. And what we do, we draw the edges between the nodes if there is a binary constant. Like if you remember that in the last class we talked about examination scheduling. So certain exam cannot be scheduled on the same day. So if it is a binary, so when I say that these two exams cannot be conducted on the same day, we can represent such a constraint by a edge on the graph. And sometimes you may not be able to represent the constraint as the edge, simple edge. It will be kind of a hyper edge when an edge is connected to more than two nodes. So that kind of scenario we say that we require hyper edge. So that is our first step. So we need to create a graph, and we have to initialize all the domain values. Once we do that, then we have to reduce the valid domains. What does it mean? That when I assign all the variables in the possible domain, then if two nodes cannot take the same values, then we can update the domain variables. So let's say I cannot assign 1 here maybe, and I cannot assign 2 here by some constraint or something else. Then I should remove this 1 from this domain, and I should remove 2 from this domain. So reduce the domain values of the variables, and in order to remove that one, we need to use some kind of a check called node consistency, or the arc or the edge consistency, or the k consistency. So these things we have to look. So what are the meaning of this one? We will come back at a later slide. So the basic idea is that if so from the domain I will try to remove some of the values so that my search space is actually reduced, and I will keep on doing so till I cannot reduce any further. So I keep on reducing the domain values, and I will stop only when I cannot reduce any further. So if I find a solution or if I cannot find a solution or no consistent solution is present, then we can actually terminate. So this constant propagation is one of the important step in solving the problem. The last thing is, once we go ahead for the constant propagation, after doing that stuff, we can have several choices to make, and then we can apply the normal search strategy to solve the problem. So we use the typical search strategy for finding the solution, and if this constraint graph that we generate has a special structure, something like if it is a tree or the perfect graphs or the interval graphs, then search algorithm can be made simpler and can be found, the solution can be found in polynomial time. But for a general graph, when we apply the traditional search, usually the problem is in the exponential domain. So so the strategy that we, for a general graphs, the strategy that we are going to take is called the backtracking scheme that we will be employing. And when we do the backtracking based search stuff, then we have to do few other things, like in what order we are going to explore the children. We can actually do some kind of a forward checking or the look ahead, so that we can reduce the search space. And this forward checking is something, it's like a dynamic constraint propagation. So when I plan to do certain things, I just take a look that how that is going to affect my solution, and if I can predict early that this is not going to lead any solution, or if this can lead to a solution, then I can save time and effect. So the main motivation is to prune the search space. And finally, also we can solve the problem by converting the CSP problem into a SAT problem. So we'll not look into this stuff in this lecture, but this can also be done. So these three are the major steps that we need to follow. So the one obvious question is that we can use the traditional search technique to find out the solution. Yes, of course, but the thing is, the normal search or the naive search may explore lot of unwanted nodes, and that can take a significant amount of time. But if we use this constant propagation technique, we can reduce the search space to a great extent for certain scenarios. So therefore we are interested to go ahead with CSP and particularly the constant propagation, so that we can improve the performance of the solution. Now to model this problem, to model the CSP problem as the search problem, we have to have the same thing that we have seen for the search mechanism. Like when we try to solve a problem using search, we need to define an initial state. So typically it will be all the unassigned variables that are available to me. The second is we have to define the state, which will be the partial assignment of the variables. And then we have to define the successor function. That means from a state, how can I generate the next state? So what would be the function, like on what variable I can choose a particular edge, and if I choose this one, then what new state I will reach. So for example, like if I look into the exam scheduling problem, then I have no schedule at this place, and then I can say that I choose for subject C1 on the day 1. So that is my choice, and once I move to the new state, then here I have a partial assignment like C1 is equal to D1, C2, C3 are still unknown at this state. And of course we have to have a defined goal state so that we can identify that when we reach to the desired one. So in this state all variables should be assigned and all constraints should be satisfied. So there can be a cost for each of the path that we choose depending on the problem, and for our case today we will see the uniform path cost. So it's a basic search strategy that we can actually use to find out the solution. Now the main step is the constraint propagation. So in constraint propagation what we need to do is we have to eliminate some of the values from a given domain. So that is the basic motivation. So the steps that we have earlier said, like we first construct the constraint graph. So let's say I have variable x1 for one node, x2 one node, x3 another node, and maybe this can take values, let's say d1, d2, d3 and so on. Maybe this can take value d2, d3, d4. Let's say this takes d1, d4 for some domain that is being assigned. And there can be some kind of a connectivity, that means these two values cannot be same, or something like x1 less than x2, or some kind of a constant that I can actually specify. So first of all, like we need to handle the constraints. So the constraints can be an unary constraints, like if I specify xi is not equal to 9, that means let's say if I say x1 is not equal to d1, I can simply remove d1. So I can reduce the search space, or I can reduce the domain values. For binary constraints we can say that xi is not equal to xj, or maybe I can say xi is less than x2. So if that is the case, let's say d1 is 1, this is 2, this is 3, and let's say this is 2, this is 3, this is 4. So the thing is all values actually satisfy that stuff. Now it can be a situation like I have 1 here as well. Let's say here I have d1 as well, so which is effectively 1. So now the thing is I can simply say that if x1 is less than x2, then x2 cannot be 1, because if I choose 1 then I do not have any values on for x1, but I can choose 1 for x1. So I can reduce the domain values, and similarly for the higher order, so for that we need to use hyper edge, and based on that we can actually modify some of the values. So that is the basic constraint. Now based on that information we can go ahead with the node consistency, arc consistency and path consistency. So this will be the given as inputs, or from the model we write those constraints, that constraints needs to be satisfied for finding out an optimal solution. Now we go ahead with the node consistency, which I was telling earlier, like if I say xi is not equal to 9, then I can simply remove 9 from the domain stuff. So which is that is nothing but the node consistency, because I want to make all the nodes to be consistent. So what it says that for every variable vi, remove all elements di that do not satisfy the unary constraint for the variable. So if this is given to me, then I should remove 9 from my list. So if 9 exists, then I should remove that one, so that will reduce the domain values. So, and that is the most simplest way to refine the stuff. And so this is the very first step. So we call it's a node consistency, and that is we use only the unary constraints. Now from unary constraints we go for a binary constraint. So for binary constraints we will have an edge in the constraint graph. Now on this binary constraints we have some values here for this node, and again we will have some values for this node. Now what we will do, we check for this arc, whether this arc is consistent or not. So like say let's say this takes value 1, domain value is 1, and this takes domain value 1, let's say for the time being, and my relation that expect x1 is not equal to x2. So definitely this arc is not consistent because both of them can take only 1, and so I do not have any solution for this one. So but let's say if I have say 1 and 2 here, so let's say I have here 1 and 2, and this is 1, then then this arc is consistent because if I choose 2, I have some other value other than 2 on this node. So this arc is consistent in that way, but when I choose 1 for this node, then this is not consistent. So the thing is, what we will try to do is, for every element of xij of di, so I take a value on this part. So when I take xij, that means I take one value and and I look into I'm looking into this edge. So I take for every element xij of di, for every edge from vi to vj, for every edge from vi to vj, I can remove xij if it has no consistent value in the other domain satisfying the constraints. So that means if I choose 1 here, then this is not being satisfied, so I can remove 1 from this node, because I know that I cannot choose 1 here because that is conflicting with the other one. So I remove this 1 from this domain. So and I can continue with this stuff until no further reduction happens. So this is an arc consistency. So we try to reduce the domain values by looking into the set of edges by every edges individually. So this is the thing. Another thing, an extension of arc, is the path consistency. So what we will try to do is, let's say I have x1 less than x2 less than x3 less than x4, let's say, and let's say all the values have the domain from 1 to 4. Fine. Then if that is the situation, so what I will do, I will look into this stuff. So they are connected through some edge, and that relation is less than. Now if I look into this path, then what I can say, that if I choose 1 here, then I cannot choose 1 here, I have to choose 2. If I choose 2 here, I have to choose 3. If I choose 3, I have to choose 4. So so there can be many ways I can choose. I can choose 4 here, I can choose 4 here, I can choose 2 here, I can choose 1 here. But if I choose this set of values, then it is not consistent. Along the path, it is not consistent. And so the thing is, here we are looking into consistency across one edge. Here we'll be looking the consistency along a path. And so that is the step. So for every element yij of di, choose a path of length L with L variables, use a consistency checking method similar to the above, and reduce the domain if possible. So we can extend this arc consistency idea into path consistency. Now the way we actually execute this arc consistency, that we are going to see with an example as well as with an algorithm. So the the way it actually works is as follows. So we initialize a queue. With all the arcs in the CSP. So that's very simple, and we iterate till the queue is empty. That means we have checked all the edges and we cannot reduce any further, and then we will stop. Now from the queue we choose one of the edge, and then we just check that whether we are updating the domain values of xi or not. So we choose one of the edge, let's say we choose xi and xj, this edge. So it will have some domain di, it will have some domain dj. Now what I need to do, I have to check for all the variables d1 to say, let's say dk or whatever may be. For every such value there exists a consistent value here. So when I choose d1, maybe there should be, let's say, some y1 that satisfy this constraint. When I choose dk, there's, let's say, there may be a yk that satisfy the constraint. So yk can be equal to y1 also, whatever may be, but for every values of di, there exists one such value. So if it exists, then we cannot reduce this one, and if we update this domain, let's say for d1, if we choose this d1 and we find that there is no consistent solution in the dj, then if that is the case, then we can discard d1 from the domain, because I know that if I choose d1, then I cannot have a solution. So if I modify these domain values, so this revise returns whether I am updating the domain values or not. So if I update the domain values, and then it may happen that the domain becomes null, that means there will be no more solution possible, because then we can simply return false. That means we could not find any solution. And if it is not the case, that means there are some other values exist, then what we will do, we look into the other nodes, other neighboring nodes of xi. So some node will be sitting here, some node will be sitting here, and so on so forth. And it may happen that we have already explored these edges. It may happen, or some of the edges I may not have explored as well. Now if I modify this one, then what I will do, I will add these edges, the edges that I have looked into earlier, into the queue again. So that is the stuff for xk. For xk, that is the neighbors of xi other than xj, because we are working with xj, we add xk and xi to the queue, because this edge may have been reduced, or this edge or this constant was updated by looking into these values. So now we are reducing these values, so we have to recheck that stuff. So that is the basic idea for AC3, and now we will elaborate how we are doing the revise. Now for revise, what I need to do, for revise I have two nodes. So this can take value d1, d2, d3, and let's say this can take value y1 and y2, so on and so forth. Now what I will do, I choose one value of here and I try to find out any consistent value exists here or not. Similarly, I take d2, I check any consistent value exists or not. I take d3 and I check if any consistent value exists or not. So what I can do, I can take d1 and I compare with y1 whether it is consistent or not. I can compare with y2, I can check the consistency or not. If it is not consistent for all the values, then only I drop, and if there exists at least one satisfying stuff, then I cannot delete that one. So therefore what we do, for each x in di, if no value y in dj allows xy to satisfy the constraint between xi and xj, so no value of y in dj allows xy to satisfy the constraint, then only I delete this part and I revise, I make the revise to be true, and then I return that one, and I continue the AC3 process. So that is the basic strategy of our checking of our consistency. So now can you tell me what will be the complexity of this algorithm? The thing is, if we want to analyze the complexity, the idea is, let us first look into how much what is the time complexity for this one. As we have said, for every di we look into every yj whether they are compatible or not, and let's say both have the domain size as d. So I have to check for each and every pair. So the complexity of revise is nothing but d squared, because when I call for this one, then I have to check for the consistency between each and every pair, so it will be effectively d squared. Now coming to this part for AC3, the thing is, we are removing an edge from the queue, and that some edge can get added into the queue. Now the thing is, what is the maximum number of times an edge can get added into the queue? So it will be added in the very beginning, that's very sure, and how many times it can get added in this part. So this can get added d number of times, where d is the domain for the variable, because the thing is, whenever whenever I remove a variable, when I remove one values from its domain, in the worst case this edge can get added into the queue. So effectively an edge can get added maximum of d number of times. Fine. So that is d, and we iterate the whole stuff for all the edges. So if I have e number of edges, then effective complexity will be my e of dq. So this iterates over maximum of ed times, because all the edges and each edge can appear d number of times, and for each of these combinations I spend d square amount of time. So effectively it will be edq. So this is the worst case complexity. It can be much less in many practical scenario. So now let us take an example. So in this example we have four variables a, b, c, d. The domain is 1, 2, 3 for each of the stuff, and the constraint is a not equal to b, c less than b, and c less than d. So so the thing is, I will have I need to construct the constraint graph, and I have to find out the edges, and then we can proceed for all the stuff. So let us start with this one. So we create a queue with this set of edges, and here what do we do? Each edge has been added twice, because when I have a connection something like this, I have to check the consistency between these variables along with each of these variables, and similar for x1 and x2, I take values from x1 and I check whether it is satisfying or not. Similarly, at some point of time I have to check this value and whether this satisfies it or not. So effectively we add two edges, all the edges will be added, and here we use some kind of a direction notion. That means when I'm looking into a, b, that means I will try to check the values of a's are consistent with b, and when I look into ba, I will choose a value from b, and that should be consistent with a. So initially we will have 6 edges and then we have to run the AC3 steps. So we pop AB. Now if you look into AB, then I have this situation. So A and B, and there is a relation between this, it is not equal, and this has domain 1, 2, 3, this has domain 1, 2, 3. Now for 1 I can have a satisfying solution 2, for 1 I can have a satisfying solution 3, for 2 I can have 1 as a satisfying solution. When I choose 3, I can choose 2 as my satisfying solution. So therefore I don't have anything to update here, so nothing is getting updated, so it's fine. So I can simply remove AB and Q will become BA, BC, CB, CD, DC. Now we pop another edge, let's say BA, and since these are not equal, so it will remain the same. I can simply remove BA. Now I come to BC. So if you look into BC, so B has BC, B has a domain of 1, 2, 3, C has a domain of 1, 2, 3 and they are related, so B is greater than, so there is a relation something like this. Now I have to check for consistency for each of the values, so I take 1 and I find nothing in C, because if I choose 1 then there is no solution for C. So I have to remove this 1 from my the domain values. If I choose 2 I can choose 1, if I choose 3 I can choose 1 or 2, any one of them. So I have some satisfying solution, so I have to remove 1 from its domain value. Now the thing is, if you look into this constraint graph, then A will be also connected to B and there is a relation not equal to. Now when I update this domain of B, then I look for all the neighbors of B other than C in this case, and I add this edge once again, because I am removing this one, so it may happen that I have to recheck the values across this edge, that whether it's still satisfying or not. So effectively I will add the appropriate edge. So I will add AB, because I have to recalculate or reevaluate AB edge. So we updated this DB domain of B and we added AB to the Q. So then the Q becomes something like this, and we can continue in doing so. Then maybe we will choose CB. If we choose CB, then probably I can remove 3, DC will get updated with 1, 2 and no change in the Q, because CD, so D is not, so I'll be looking into all the neighbors and CD is already there, so therefore I do not need to change anything. Now I pop CD and I find that this is fine, so it will be there and I can continue in doing so. At some point of time we choose DC and the domain of D will be updated with 2, 3 and then we will left with only AB and no change in AB, so we can stop at that point of time. So we can continue in this way. Effectively I will get this as my final solution after running this AC3. So let us take an example how we can use this kind of stuff to find out the solution. So let's look into this Sudoku problem, and let's say we want to identify the value of x and y. Now what are the constant I can write? So x can take value between 1 and 9, of which it cannot take 1. So let us so for the Sudoku the conditions are as follows, like all the values in this square or every square of 9 grid which has been demarcated with the bold line, they will have all different values. All columns will have 1 to 9 and any rows that I choose will have 1 to 9. So that is the constant that I have. So now let us look into this x. So let us look into this block. So let me rewrite it a little bit. So I have x, it can take value 1, 2, 3, 4, 5, 6, 7, 8, 9, and now if I look into this middle grid, then it cannot take value 1, it cannot take value 2, it cannot take value 7, it cannot take value 8. Fine. If I look into this column, then it cannot take 5, it cannot take 6, it cannot take 2, which it cannot take 8, it cannot take 9, it cannot take 3. So effectively we are left with only choice with 4. So effectively this will be my final solution. So we do not have to for this example we do not have to do any kind of computation. We just, once we apply the R consistency or the constraints, I will be able to find out the solution. So let us look into y. What is the situation for y? So let me write for y. So the values that it can take 1, 2, 3, 4, 5, 6, 7, 8, 9. Fine. Now if I look into this grid, then I can see that I cannot take 1, I cannot take 2, I cannot take 3, I cannot take 6, I cannot take 9. Fair enough. Now if I look into this row, then I cannot take 5, I cannot take 1, I cannot take 3. Now if I look into this column, then I cannot take 5, I cannot take 6, I cannot take 2, fine, I cannot take 8 also. And since 4 is selected for here, so effectively I cannot take 4 as well. Now if I'm trying to resolve this way, then x will be resolved to 4, so effectively y will have only value 7 to take. So by applying this consistency, we can find out the solution, but this is for a simple Sudoku problem, so it may not be always possible. Just to eliminating in this way will get the solution, so there may be some complicated scenario as well. So I will give you one simple example. Let's say we are trying to find out the solution for this row, okay, and let's say this cell, after applying some kind of a R consistency, I observe that this can take value x1 and x2. Let's say this can take value, say x2, x3. Okay, let's say this can take value x1, x2, x3, something like this. And let's say this can take values, let's say x1, x2, x3, x4, x5 for this one, and similarly for this one as well. Now if I have this situation, then I can actually conclude that x1, x2, x3 will not be, any one of these three values cannot be placed here. Why? Because if you look into these three cells, you have three choices and so you have you have to fill with three numbers, and the choice range that you have here is exactly 3. So effectively x1, x2, x3 will go into this one, and these two cell can only take value x4 and x5. So here what we need to do, so if we look into the arc consistency, we will not be able to find out. We have to look for more than two cells to figure out such constraints. So this kind of constraint makes the Sudoku more challenging and interesting one as well. So this constant, so AC3, when we check for arc consistency, it is a very useful one, but it has some kind of a limitation. So one of the thing is, once we run this algorithm, there can be just only one solution. That is the best thing. There can be more than one solution, still this is okay. And the other thing is, there may be no solution, but it fails to identify. So this is the most critical scenario. So this is not the thing that you would like to encounter, or if you can find it out, then it will be easy. So the example that I gave for Sudoku, which is somewhat similar to that one. For example, let's say I have this situation that I have 3 variables, and all these 3 variables have certain kind of a constraint, and they can take either red or the blue. Now if you apply arc consistency between every edge, so if I choose red here, I can choose green here. If I choose blue here, if I choose blue here, I can choose red here. Similarly, when I look into this one, I have a consistent solution for each of those variables. So this is because we are looking into each arc. If I look into these 3 nodes together, then we can simply say that no solution is possible. So that is one of the major issue with AC3. But this algorithm runs in polynomial time. If you increase the if you increase the number of arcs, that means if you are checking for a consistency across a path, then the complexity grows, and most of the time it will go into the exponential domain, because you have all possible combinations and that you have to explore. So which may not be feasible, or which may not be good in terms of the timing requirement. So now let us look into our old problems, examination scheduling. So so the question is like this. So you are given a set of students who have opted for certain subjects. The goal is to whether we can schedule all the exams in 3 days or not, and we have seen the constraint graph earlier. So in order to find out the solution, so one of the naive strategy is we can apply the search technique like BFS or the DFS. So if we apply BFS and DFS technique, it can be it may be a problematic in the sense that complexity can be very high. So let us look into one such example. So in order to apply the search technique, so we start with an empty list or empty assignment. Then from this empty assignment, we try to explore all possible assignments that are feasible. Now what is the options we have? So we can choose in this way. We assign C1 on the D1, we assign C1 on the D2, and so on so forth. Similarly, C6 on the D3. So the number of choices that we have here is, if I have n number of exam and if I have d number of days, then effectively I have nd number of choices. Now from each of these option, again I will have that many I have to explore for the other stuff. Now if I choose C1 equal to D1, so I have frozen for C1. Now C2 can take D1, C2 can take D2, and so on. Similarly, C6 can take D3. Similarly for the other stuff. Now in this level, how many choices do I have? For every node I have actually d options, because I can assign the day, and now I have n-1 number of stuff. So effectively the number of nodes that I need to explore is this much. So I can continue from here and so on. The effective complexity then will become is your nd times n-1 times d, and so on and so forth. Effectively it becomes n factorial and d to the power n. And here I have only 3, so it will be n into n-1 into n-2 and d cube, or if you in the worst case it can go up to this way, so which is basically an exponential number. And the number of possibilities that we have here is effectively the search space should be d to the power n, because each exam can be held in any one of the d days. So if I have d days available, so the actual space search space should be d to the power n. But the way we have developed this strategy can lead to a complexity something like this, so which is more than the actual search space. The reason this is happening because we have chosen a very bad way to search this space. So instead of allowing the other subject to be chosen in this level, we can restrict only one subject at each level. If we do that stuff, then we can reduce the complexity significantly. Then what will happen? In each level I have d options. So in this level I have d option. Again for each one I will have only d option. So I can reduce the search space to d to the power n. So if you use a naive DFS and BFS, it can perform very poorly. So you have to be very, very careful. Now the thing is, what we need to do is we need to use backtracking based method, because we choose some value and then it may happen that we may not find a solution, we have to backtrack. So if you so here what we have done, we have explored the whole space in the BFS manner. That means the whole tree will be generated. So that is again even not required. So we can actually apply DFS. So we start with some partial assignment. We come here, we come to the leaf level, and if we find no solution, we go back, we explore the other path, and so on and so forth. So in this way we can actually use. So DFS is better in that sense because the space complexity is less. So what we do here is we do a kind of a backtracking based methodology which is based on the DFS like technique. So what we do, we use one variable at a time. So we choose first C1 and we order the variable. So we basically we need to do some kind of a ordering of the variables. So maybe we can order as like C1 equal to 1, C2 equal to 3, or we can order in this way. So when we order in this way and when we order in this way, after the completion of this and completion of this, we will have the similar stuff, because that is the basic thing. So we will have a similar situation, that one. Now once we have some partial solution, then what we do, we check for the constraints. So when we choose a new value for a particular variable, we try to explore that it is not affecting the previous assignment as well. Like if I have a graph something like let's say let's say this is C1, C2, C3, and I have assigned red, I have assigned green here, and I have choice like red, green, blue. So I started with empty list, then I have chosen C1 equal to R, then I have chosen C2 equal to G, let's say. Then I have 3 options for my C3. Now when I'm trying to see C3 equal to R, I will cross check that whatever assignment already have been done, it is not violating, because if it violates, then I should not explore the tree below it. For this case there is nothing to explore, but let's say I have another tree, bigger tree in this position, and if I assign red here, then it violates, so I should not explore this portion of the tree, and that can save significant amount of time if we can prune a large chunk of the tree. So if I cannot assign R, I will go back and then I will explore with new alternatives. So this way the backtracking method actually occurs. So the algorithm works as follows. So if the assignment is complete, then return success and assignment. Otherwise you choose one unassigned variable, and for each value of the domain of the variable that you have chosen, you start check for the consistent with the assignment. So the value that you are choosing, it is consistent with the assignment already. So whatever you have we have made assignment, and here you are making a new assignment, so this value is consistent with this whatever choice you have made. And you add that variable to the assignment, and again you do it recursively. At some point of time, if you find that there is a problem, you cannot assign, then you return failure and return the assignment. So now the question is, the most important question is that we are choosing an unassigned variable at this stage. So which variable we should choose for assign to be next, and then the thing that we need to look into, which value we should choose for that variable. So, and also if we can detect any early failure, then that can save a large amount of time for our problem. So there are certain basic rules which you can actually employ. That does not guarantee that this is the best, but typically we use this kind of strategy for our solution. So we will see those things a little later. So now let us look into a complete example for backtracking. So this is the famous 4 queens problem. So it's a smaller version of n queens problem. So I have been given a 4x4 board. I have to place queens in such a way that no queens are attacking each other. So for this example, if I place in this way, then these 2 queens are attacking each other, these 2 queens are attacking each other. So this is not a valid solution. So I have to place 4 queens, and the queens can move in the horizontal direction, it can move in the vertical direction, it can move in the diagonally as well. So parallel to the principal diagonal and off diagonal. So what we will do, we will make some. So first, we do not have any option, so we will choose the first place to put 1 queen at this place. Now when I choose this queen, then I know that I cannot place a queen here, because if I place, then it will be attacking the first one. It will be, if I place here, it will be again attacking that one. But here I can put a queen here, because then it is not conflicting. So I can choose my next queen to this place. Fair enough. Now, so when the other important thing, because when I try to place 4 queens, that means, and each queen can move in row and the column wise and the diagonal wise, that means every row and every column will have exactly 1 queen. So we are exploiting that fact. Now coming to here, so we are trying to place a queen in the 3rd column. Now if you try to put a queen in the 3rd column, then I cannot put any queen here, 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 because some queens are there that attack this column. So effectively I can say that I cannot place any queen on the 3rd column, so I have to go back and I have to choose alternative for the 2nd column. So there is no solution, so I have to go back and I have to change the option. Then I choose the 4th row of the 2nd column. Now once I do that, then again I have to place another queen in the 3rd column. So I cannot place anything here, I can place here. Also I cannot place here, I cannot place here. That's just for your information. So I can place the next queen there. Good enough. Now the next queen that I need to put on the 4th column, I cannot put here anything, I cannot put here, I cannot put here, I cannot put here. So there is no solution in this path. I have to go back and I have to change the previous choices, and if the previous choice has no other option, then I have to go previous to previous and modify that one. So there is no such solution. So effectively I have seen that earlier there was no solution. So for the third column for the third column there is only this viable position, and in the second column this was the last, so there is no other option. So I have to go back and I move it to the second position of the first column. So I keep on exploring in that way, and if I try to do that, then I find this, and then I can place the final one in this way. Now if you look into this one, then I reach to a desired settings, and in this settings no coin attack each other. So this is kind of a backtracking, and if we can prove early stage, then it can save a lot of time for exploring the state space. Now when we choose the variable that I was talking earlier, like the variable ordering, so which variable I should choose. So one option is we choose it randomly or some static ordering. That is not always a good choice. Then we can choose the variable which has the minimum remaining values. If I choose a variable which has minimum remaining values, that means we are reducing the search space, because it is the most constraint variable, so it has least number of legal values. So I have less options, so my search tree will be reduced. And we can also go for degree heuristic. So variable with the largest number of constraints on the other assigned variables. So these are some kind of a heuristic, so which has the maximum degree, so that it can constrain maximum number of other variables. Now once we freeze the variables, then we have to choose the value, which value we should choose. So we should choose a value which is least constraining. The reason choosing the least constraining value is that we are trying to find out a solution. If I choose the most constrained value, then we may not find out a solution. We have to again explore with the other one. So we try to choose the least constraining value so that it leaves most number of choices for the neighboring variables, so that I can find out a solution. So these two are the basic choices that most of the time people use in their approach. And when we do this kind of strategy, what we do some kind of a forward checking. So forward checking can help in pruning the search space. So when I select one value, I try to see how is the situation or how I can proceed further. So for example, so this is the examination scheduling problem, and this is the constraint graph that you can see here. And we have all the values initialized, all variables are initialized with red, green and blue. Now in the first step we choose any value for C1. Let's say we choose red for C1. Then definitely we'll look into how the other variables are stays when we assign this value. Now if we assign red here, then from C2, C3, C5, C6 I have to remove red because I cannot assign any further. Now let us choose C4 and let's say we assign value green for C4. Now we try to see how is the situation. Now what will happen, we will find that C2 and C3 will left with only one choice, and that is blue. And if you look into this graph, then you will find that C2 and C3 has some connecting edges, so that means there will be no solution. So that means if I use C1 red, C4 green, then even before assigning any values for C2 and C3, I can upfront say that there will be no solution in this assignment. So we should go back and we change our previous decision and we explore with other stuff. So this kind of forward checking can help significantly in improving the runtime. And there are few special cases which we'll like to highlight. Only thing, we'll not go into the details. So the general CSP problem is NP complete, so no known polynomial timing algorithm exists as of now. And for certain kind of a graph, like the graph that you see in the slide is a tree, or the graph like a caudal graph or the interval graph, for this kind of a graph, it can be solved in polynomial time, so that you can explore on your own. So in this lecture what we have seen is how we can solve CSP. So the overall idea for CSP is that we have to construct a constraint graph, then we have to go for node consistency, you have to go for arc consistency, that is nothing but the constraint propagation, and then we go ahead for the search stuff, or we use the backtracking based method to find out the solution. So one of the advantage of over the traditional search approach is, for traditional search it searches almost like a blindly, but when we have these constraints, we try to restrict the search space by pruning some of the inconsistent assignment, and that we try to figure out as early as possible, and based on that we try to prune the search space. And in many problems that we have observed, that it can reduce the search space significantly. So therefore CSP is one of the popular technique in AI based method when we try to solve any problem, any satisfiability problem or any problem for the optimization. But for optimization problem we may have to do few extra work because it has to explore all possible solution. So that is that you can refer from the book. So thank you very much.